This is the Electric Field 2 lab. If you are all caught up on lecture videos, then you should be able to answer the questions in this lab. I'm going to give you some help for the first problem in the lab. We have our equation here for the electric field, and remember this came from the first equation that we had for the electric field, and then we made a small piece with a small charge, an infinitesimally small charge dq, and then we said if we add up the charge from each small piece and make the dq really, really small, then it becomes an integral, and that gives us this equation here, and the r hat is still a unit vector pointing in the direction from the charge to the point of interest, and r hat probably depend on which small element you're talking about. So as you integrate, the r and the r hat are going to change, which means unlike the q, you cannot pull them outside the integral. So we're going to have to write the dq in terms of usually either ds or d theta. Okay, so the first problem in the lab is actually almost the same as problem 56 in spiral physics, except that in your lab for that first problem they give you numbers, and problem 56 is a symbolic problem. So let's try and do both problems at the same time and compare the two. So starting off with your lab, we have a thin 10 centimeter long plastic rod, and it has a charge of 5 microcoulombs uniformly distributed along its length. We would like to determine the electric field 10 centimeters above its center. So the rod is 10 centimeters long, and let's call that L. L is equal to 10 centimeters. We want to find the electric field 10 centimeters above its center. Well, if this is 4 blocks, the point of interest is up here. And we have a charge of 5 microcoulombs. Okay, and before we go any further with the lab, let's take a look at problem 56, where we have a plastic rod with a charge minus q and uniformly distributed along length L. Find the electric field at all points on the y-axis above the rod. So we're going to skip the first step because we haven't got to that in the lab manual yet. We will need to carefully identify and label y, which is the location of the point of interest. So what changes here is that this distance now is just y. But after we finish solving the problem, we can go back and we can say y is equal to, here, this distance is 10 centimeters. So if we take that and put it into our equation here, along with the other numbers we're given in the lab manual, the two should agree. Except that this charge is negative q and this was a positive charge, but we can remember that and it will be okay. Write an expression for dq, the charge on the differential element. Actually, I don't want to do that quite yet. I just want to say, I don't know, the charge is negative q and the length is L. Okay, so now moving on in the lab, since this is a continuous distribution of charge, you'll have to do an integral to find the electric field. The most important part of this calculation is determining the differential element. The differential element is a small length of the rod whose contribution to the electric field can be directly calculated. The differential element ds has been labeled on the diagram at right. The element is a distance s from the center of the rod. Note, it is extremely important to clearly label the position of your differential element. This position varies as you evaluate the integral. Okay, so they said here, when s is equal to 0, you're at the center of the rod, but it does not have to be that way. But because they said that for this problem, that's what we're going to do, but later on we're going to see how you could set that differently. Okay, so we're going to put ds here, and the only thing I would do is keep it so that x is positive where you draw ds, so don't put it on, you could put it on this side of the rod, but I think it is easier to put it on the right half of the rod. So this is s. Okay, so we have carefully identified and labeled s, the location of the differential element. We also carefully identified and labeled y, the location of the point of interest. And let's move on in the lab. To find the contribution to the electric field due to this element, we must calculate dq, the charge on the element, r, the distance from the element to the point of interest, and r hat, the unit vector representing the direction from the element to the point of interest. Those are all things that are in your equation here. So basically, if you want to use this equation, you have to figure out what each piece of that equation is. To determine the charge on the differential element, we will first define a linear charge density lambda. For a uniform distribution, lambda is defined to be the ratio of the total charge on the wire to its total length. What is lambda for this rod? Well, they tell you that's Q divided by L, and Q is 5 microcoulombs and L is 10 centimeters. So that's 5 microcoulombs per 10 centimeters, and the units just look a little funny there because it's microcoulombs per centimeters. Micro is 10 to the negative 6. So this is 5 times 10 to the negative 6 coulombs. And 10 centimeters would be 0.10 meters. If you want to leave it as centimeters, you could do that. Your limits of integration, which come from the length of the rod, you would either be in centimeters or meters. But if you're going to keep this in centimeters, then I would keep all the other length measurements in centimeters also until you get to the very end. Or you could change them all to meters now. Okay, so now for problem 56, we want to write an expression for dq, the charge on the differential element. First, they had us do lambda here. Actually, so let's go back here. Use your value for lambda to write an expression for dq, the charge on the differential element of length ds. Well, lambda is not only equal to q over L. If you look at a small piece, it's the charge on that small piece divided by the length of that small piece. And so we can say dq is equal to lambda times ds. And then I would go ahead and take the lambda that you have here and put it in here. Actually, before we do that, I would say this is 50 times 10 to the negative 6th coulombs per meter. Then take this and put it in here, and we have dq is equal to 50 times 10 to the negative 6th coulombs per meters times ds. Now, if you didn't want to plug this in until the end of the problem, I would be all right with that. So if you want to just say lambda for now and then plug it in afterwards, you can do that also. Okay, so here, write an expression for dq, the charge on the differential element. Well, lambda is equal to charge per length. It could be the whole charge divided by the whole length, or the charge on a small piece divided by the length of the small piece. And so we have dq is equal to lambda ds. And you could leave it like that, or you could say if we have a charge of negative q and a length of L, lambda is negative q over L. So this is minus q over L ds. Just be careful here because for lambda, we usually say q over L, but in this case the charge is equal to negative q, so make sure you take care of the signs. Okay, for part 3, we want to write an expression for r, the distance between the differential element and the point of interest. Now they have you doing the distance, but if we make a vector here, I'm going to use this picture down here since I haven't, this one's a little cluttered already. Okay, so here's our point of interest. The vector r goes from the charge to the point of interest, just like it did back with our other equation for the electric field. This one here, r goes from the charge to the point of interest. The vector r goes from the charge to the point of interest. From the charge to the point of interest. Now it is important to correctly identify and label the location of the point of interest because you're going to need that for the vector r. Let me write what the vector r is first because I think that's helpful before we look at the distance. The vector is going to distance in the negative I hat direction, and that distance is s, so that's minus s I hat. S is positive because it's over here, so it's minus s I hat, and the distance it's going up, well, in this case is 10 centimeters, so that's plus 10 centimeters in the j hat direction, or if you're converting everything to meters, you could say minus SI hat plus 0.10 meters in the j hat direction. Okay, and either keep everything in meters or keep everything in centimeters until the very end. If you have everything in centimeters at the very end, then you're going to need to convert it into meters. But if you want to keep it in centimeters until then, just make sure everything is in centimeters so the units work out. Okay, write an expression for r, the distance between the differential element and the point of interest. Well, if this is my vector r, let me redraw it here. And this distance is s, and this distance is 10 centimeters, then that length would be equal to the square root of s squared plus 0.10 meters squared. Okay, and then let's go to problem 56. Write an expression for r, the distance between the differential element and the point of interest. So from the differential element to the point of interest, that vector is r. I'm going to write the vector first. So the vector r is equal to minus s I hat. In this case, it's not 10 centimeters, it's just y, which I think makes it easier. And then the distance r, that would be, remember, the magnitude of the vector. That's the square root of s squared plus y squared. And it doesn't matter that s is negative because we're squaring it anyways. Then I want r hat, the unit vector representing the direction from the element to the point of interest, which has the same direction as the vector r. We just need to divide it by the magnitude to make it a unit vector. So r hat is equal to the vector r divided by the magnitude. So the vector was minus SI hat plus 0.10 meters in the j hat direction, divided by the magnitude, which is s squared plus 0.10 meters squared. Okay, and then for problem 56, r hat is equal to the vector r divided by the magnitude of the vector r, so that's minus SI hat plus yj hat divided by s squared plus y squared. And you can see for r hat, you should be able to see for r hat, there we go. If you say y is equal to 0.10 meters, you get the same thing for the lab as you do for problem 56. Okay, so then on the next page, use your results from the previous 3 questions to write an integral expression for the electric field, choosing the limits of integration carefully. Determine the electric field 10 centimeters above the center of the rod. So here's our equation that we're using. So the electric field is equal to the integral of k dq over r squared in the r hat direction. So now I should just be able to take what I have on page 2 and plug it into my equation here, and then I should be all set to do the math in order to figure out the electric field. So I also need to remember to carefully choose the limits of integration. So I'm going to save that for the end. K is just a constant, and that can come outside of the integral. R squared, that would be this squared. So that would just be s squared plus 0.10 meters squared. So it was the square root, but then I squared it, so now it's not the square root. And then dq is equal to this. So that's 50 times 10 to the negative 6th coulombs per meter. And then I have the ds, which I'm going to, I still have to do the r hat. I'll put the ds out here. Okay. Then r hat, there's my r hat. That's a minus SI hat plus 0.10 meters j hat. And then I have the square root of s squared plus 0.10 meters squared in the denominator, but I already have that here. So just like for this equation here, we have 1 from the r squared. Then we have the same thing to the 1/2 power from the r hat. So if you multiply them together, you add the exponents, and that becomes to the 3/2. Okay, and now we have to carefully choose the limits of integration. We're integrating over everywhere where there is charge, so from one end of the rod to the other end of the rod using the s that you have when you're on this end of the rod. S would be equal to negative L over 2. When you're at this end of the rod, S is equal to positive L over 2. The rod is 10 centimeters long, so when you're over here, S is equal to negative 5 centimeters, and when you're over here, S is equal to positive 5 centimeters, except that I wrote everything else in meters. So this would be negative 0.05 centimeters, and this would be positive 0.0, whoops, not centimeters. Okay, so this is just meters. I can pull out the k, because that's just a constant, and I can pull out the 50 times 10 to the negative 6, and then I really have two different integrals here. Isn't that fun? So this is k, I could put in 9 times 10 to the 9th for k. Okay, and then we have the first integral. You don't have to write it this way, but maybe it's easier to see it this way. So you have the negative SI hat. So it would be this times this for the I hat term, and in the denominator you have s squared plus 0.10 meters squared to the 3/2 ds. And then you have the other term, which comes from multiplying this by this. That's plus the integral 0.05 meters to 0.05 meters, 0.10 meters in the j hat direction, divided by s squared plus 0.10 meters squared to the 3/2 power ds. So we got two different integrals to do there, and that will tell us what the electric field is. Okay, and then in problem 56, we need to write an integral expression for the electric field, choosing the limits of integration, calculate the integral. So this is going to be similar to what we just saw. The electric field is equal to k times dq over r squared in the r hat direction, integrated here from one end of the rod to the other end of the rod. In this case, when we're at this end of the rod, because the length is L, this distance from here to here, that's L over 2, but S is negative over here, so that's from negative L over 2 to the other end of the rod, which is positive L over 2. Then we have K times dq. dq is negative Q over L, and it just makes more sense to put the ds at the very end, so I'm going to put that over there. And then we have R squared, which is S squared plus y squared times r hat, which is negative si hat plus yj hat, divided by s squared plus y squared to the 1/2, but I can take care of that just by making that to the 3/2. And this again is really two different integrals. So I could write this as, I can pull out the minus kq over L, and then we're integrating from negative L over 2 to positive L over 2. I have a negative si hat, s squared plus y squared to the 3/2 plus the integral of negative L over 2 to L over 2. And this is yj hat over s squared plus y squared to the 3/2 ds. And the negative kq over L is in front of everything. Okay, and I'm going to pause here and do the integrals in the next video.